Hi there. Now in this video what I want to talk about is another property, and that is commutativity. And I've got a definition here that if we've got a binary operation, let's say star, defined on a set R of real numbers, then it's commutative if A star B equals B star A for all AB which are members of the set of real numbers. Now already you should be familiar with some common binary operations which are commutative, and they are addition and multiplication. For example, let's say we take 2 and add it to 3, then clearly that's 5, but you get exactly the same result if you just turn it around. 3 plus 2 equals 5. So we say that addition is commutative. Similarly, if you did say 3 times 2, then it's going to be exactly the same as 2 times 3. Both of those give 6. So multiplication is commutative. Whereas if you take subtraction and division, those operations are not commutative. For instance, if you did 2 take 3 minus 1 is different from 3 take 2, which is 1. And if you were to do 3 divided by 2, for instance, then that would be 1.5. And if you did 2 divided by 3, that would be 2/3. So subtraction, division, then not commutative. Now you may be asked to show that a particular binary operation is commutative. For example, is the binary operation star defined by A star B equaling A plus B plus AB commutative for all members A and B of the set of real numbers? Well, to do something like this, let's just start by doing B star A and see if we can prove that it's exactly the same as A star B, this result here. Well, if we do B star A, according to this rule, we add together the two elements first of all, so we've got B plus A in this example, and then we add to that the product of them. We start with a B and we get B then multiplied with A. And we know that addition is commutative, so this is exactly the same as A plus B. And we know that multiplication is commutative, so that's exactly the same as AB. And what we've got here is this result. So it's equal to A star B. So we can put that in as being the same as A star B. So therefore, what we've got is that that operation, star, is commutative. Okay? So that's a typical kind of example you might be asked, and that's how we would go about proving it. Now, there's going to be situations where you're given tables. For example, if you're given a binary operation, let's say again defined by star here, and we're told that it's commutative, then if you were to form a table with the results, what you would notice is that the elements that you put in the table would be a reflection of one another in this leading diagonal. So for instance, where I've got this green dot here, let's say L combined with M, then that would be exactly the same result as M combined with L. So in this example here, which binary operations are commutative? I've got two tables here. Just think for a moment, have a look at this. Which ones of these tables do you think are commutative? Okay, well, if we look at the diagonal through this table here, can you see that the elements A and A are reflections across the line? Same with C, and the same with B. So this particular table is commutative. So just tick that, okay? When we look at this one here, it's not commutative because, for instance, if I've got a B here, I haven't got a B in this position. And similarly, I've got the B here, I haven't got the same letter here, whether it be two C's there or 2 B's. So this is not commutative. Now I've got one more example where you're asked to complete the table so that this binary operation is commutative. So there's 3 elements here to fill in. So just give you a moment to think about that. Okay, well, if it's commutative, then we would expect a reflection then in that leading diagonal. So for this element here, we just reflect the 2 across, so that's going to be a 2. For this one here, it's going to be a reflection of that element 1. And finally, for this one, it's going to be a reflection of that 3. So hopefully you should have got those. Okay, well, I hope that's given you some idea anyway then on commutativity for a binary operation.